All right, welcome everyone to my 11.3 video. In this video, we're going to be talking about this series right here and how do we determine if it converges or diverges. And of course, spoiler alert, it's going to be the integral test. But this is actually a very special series because many series out there, later on when we get more tests, like the comparison tests or the ratio tests or things like this, right, they can be solved using these other tests. And quite frankly, those other tests are going to be a lot faster. But this is a very special series, and I'll talk about kind of variations on this series as well, because they can only be solved by the integral test. And so that's kind of what makes them special. Of course, these sorts of problems maybe disproportionately show up on quizzes and exams, stuff like this, if we want to test the integral test, because again, some of these other series, right, could be solved using a comparison test or a, one of the other tests, the ratio test, geometric series test, whatever. So again, this is kind of a very nice special series here. Before I get into that, I thought it would be a little bit fun. I have here, every once in a while, I enjoy programming with a bit of Python. And so if you guys also know a bit of coding, I guess, first of all, if you don't, I recommend that you definitely, look into it and kind of get some familiarity with it. But certainly, even if you know MATLAB or whatnot, here again, I'm using Python, but a variety of other languages that you can be using. And I thought I would just kind of model what's going on with this. So I have here our specific, it's the terms of our series. So I have 1 divided by the n times the log of n. And you can see the syntax here is a little bit strange, right? So I have this math. And this log without any other base specified is actually log base e, not log base 10, as you might expect. And so I have here running in a for loop, we're going to plug in 3, 4, 5, 6, 7, all the way up to 10. And you'll see actually it stops right before that. And then we're going to sum this stuff up. So let me just run this really quick and we can see what kind of output we get. So the first bit is if you plug in 3, into our series, again, this isn't a random series, this is the actual one that I have here. The output is 0.303 and change, right? And of course, our current sum then would just be that 0.3 and change. Then the next term, a 4, right, is going to be 0.18. And then you sum that up with the one before it, right? Because we're summing from 3 to infinity, right? And you can see kind of it is slowly growing here. And so if we go ahead and maybe let's go until 100 or so. So I'm going to sum up from 3 to 100. So here are all the terms. And oops, I'm blocking it. Go ahead and move myself. You can see after you sum up the first 100 terms, you get that this goes to 1.6. And you can see that it's pretty slow here. Let's try for 1,000. I forget. So I have this extra code, which some of you may be interested in here. I was having trouble, especially letting this go. We're going to try to go to 10,000, but it gets really angry printing so much. And so I have this thing where maybe it doesn't have to print all the time. So, okay, if we go to 1,000, we can see that we just surpassed 2. So if we sum up to 1,000, you can see what before we were at like 1 and change, right? But now we're around 2. And so, okay, let's try to do 10,000. I'm just going to change my for loop and we're going to sum up to 10,000. And at least previously when I did this, like I said, it got angry with me at some point and it just stopped and it wouldn't print anymore. So here we made it past 3,000. Maybe there aren't as many people using, this website or something. Okay, so now this is where it stopped. It got to, 3,300 and change. We got to 2.17-ish. So I found that if I only print some of the time, so let's say I'm going to print maybe 1/4 of the time or something like this. So I'm going to choose a random integer and we're only going to print it, basically 1/4 of the time. So let's go ahead, run this. And you can see it does it quite quickly here. And we get up to about 2.29. or so at the end of the day. So again, it was still summing and everything like this. It just only printed about 1/4 of the time. So, okay. And again, we got very small numbers that we're adding. So we get to about 2.3-ish. And so again, the question is, does this converge or does this diverge? Does this actually go to some finite number? Or if we add on infinitely many terms going on forever, right? Does this slowly, it must be slowly, right? Does this actually go to infinity? And looking at this right now, you might be convinced, well, it hasn't even broken 3. I mean, we're at 10,000 terms right now, and it's not even summed up past 3. And so how on earth is this going to go to infinity? And so the surprising claim is that this one actually does diverge. And this is really the power of some of these tests right here, because even with, obviously you could run this like all night or something like that, and get up quite high, but maybe it's not super convincing whether or not these things actually will diverge. It seems like it's really tapering off here. I mean, it hasn't even broken 3 yet. And so let me go ahead. I'm going to switch my computer here over to my iPad, and we're going to show how to apply the integral test to show that this one actually does diverge. All right, so here we are, same series and everything, and we're going to apply the integral test. So remember, the integral test only works under certain conditions. We need that our sequence here, right, corresponding with our series, right, needs to be positive, it needs to be decreasing, and it needs to be continuous. And so I could very easily cook up kind of a multiple choice style question, for a quiz or an exam or something like this, that gives you some function or gives you some sequence here that we're focused on, right? And asks, is it positive, continuous, decreasing in like a multiple choice style fashion, right? Where maybe you have to determine if it's not one of those 3 things, or maybe multiples, right? You could have 1 and 3, 2 and 4, like those ones that, nobody really likes these multiple choice style questions. But so yeah, so we do need to double check, right? Positive. Well, we know that certainly 1 is positive. Let me just write down here. So we have 1 is positive. Since n is going to be 3 or bigger, right? N is going to be greater than or equal to 3. So that's certainly positive. That's bigger than 0. And the natural log of n is also going to be greater than 0 because we're plugging in numbers that are larger than e. So if you remember what the natural log looks like, something like this. Oh, sorry, actually, just because we're plugging in numbers bigger than 1 is all we need. So long as you're plugging in big numbers bigger than 1, right? Because the natural log of 1 is 0. So as soon as you start plugging in 2 or 3 or 4, right, it's going to be positive. So it's positive because all of these things are positive. And so when you take ratios of positive numbers, or when you multiply together positive numbers, it stays positive. I would say that, back when we used to have in paper, paper exams or whatnot, it was a lot more important to show this, right? There was usually some points associated with showing that the integral test actually holds. And so that's why I said, we could recreate something like this, verifying that folks are still testing that it's positive, decreasing, continuous, but maybe like with a multiple choice style question. Let's do continuous next. For continuous, you usually mention where all of the discontinuities are, right? So for all of the discontinuities, this would be like if I'm dividing by 0. So if I was dividing by 0, right, n would be 0, right? So since n is not 0, that's one of the places where I would have a discontinuity, because again, I'd be dividing by 0 here. The other thing is if you plug in 1 into the natural log, right, that outputs 0. The natural log of 1 is 0. And so that would be a discontinuity. That would be another place where you're dividing by 0. And then finally, the natural logs don't make sense if you try to plug in negatives into them, right? And so the fact that n is larger than 0, that we're not trying to plug in negatives into this, or 0, right? Since these are all the discontinuities, this is all the places where the function doesn't really make sense. Well, everywhere else it's going to be continuous. So in particular, from 3 to infinity, which is of course what we're interested in, we're summing up, plugging in 3, 4, 5, 6, 7, 8, so on and so forth, right? It's going to be continuous everywhere except for at these places here. So I'll just say, since n is, I'll just use the greater or equal to sign, n is greater than or equal to 3, it's continuous on the entire interval. I'll just say it's continuous. And then finally, decreasing. Decreasing, again, we talked a lot about this in the video, pre-class video and whatnot. I gave some kind of shortcut techniques, right, in order to determine if something's decreasing or not. Again, formally, if you want to know if something's decreasing, that's a Calc 1 skill. So you go back and you take the derivative and you find when it's less than 0, right? Because if the derivative is less than 0, aka the slope is less than 0, that would mean that it's decreasing. However, we saw that if you have, for instance, a reciprocal function like we do here, right? We know n is increasing. We know that the natural log is increasing. So that means that if you take the product of two increasing functions that are positive, like we've already seen here, it's increasing. So n is increasing, natural log is increasing. I should probably say so. The n times the natural log is increasing. Having a hard time writing, apparently. And so if you take the reciprocal of an increasing function, it's indeed decreasing. All right, so we have the positive, continuous, and decreasing. And so the integral test will work for this. And remember, the integral test says that this thing right here shares the same fate as an improper integral. And so the improper integral is if you were to swap this, and instead of, summing up using just the integers from 3 to infinity, we're going to do all the real numbers. So, right, we're going to be doing the integral here. And then we usually like to write ours with x's. So I'm going to do x times natural log of x dx. And again, the integral test, because these things are true right here, we know that they share the same fate. So either they both converge or they both diverge. That's the statement of the integral test. And so in order to solve this, we're going to use a u substitution. I'm going to use u is equal to the natural log of x. So du is equal to 1 over x dx. So when I swap that in, we're going to have 1 over u. And then notice that the 1 over x dx is exactly what du is. So this is going to be du. I'm going to go ahead and solve the improper integral. So I'm going to drop my bounds for right now. And then I'm going to swap back in for x's, and I'll plug that in at the very end. So when I integrate this, I'm going to have the natural log of the absolute value of u. And then I'm going to plug in, instead of u, I'm going to plug in this natural log of x. So a little bit annoying here, the natural log of x. And again, I need to evaluate this from 3 to infinity. So if I was, sorry, I haven't really spaced things out very well. Let me go ahead and just write right here, 3 to infinity. Maybe make this an arrows to sign. And so if I plug in a very, very large number into my natural log, well, the natural log does get very, very large. Here's my picture over here. It does it kind of slowly, but the natural log of infinity, an arbitrary large number, does go off to infinity. And so we have the natural log of the absolute value of something that's infinite, right? And again, we're plugging in something that's infinite into yet another natural log, which, by the way, you're probably saying, well, why didn't you plug in the 3 yet? I can do that now. Natural log of the natural log of 3. Getting a bit ahead of myself, but the big thing is that this is going to be a constant, and we're going to end up with something like infinity minus, some constant. And anytime you subtract some constant away from an infinitely large thing, it still stays infinitely large. Again, this is all kind of, we're doing limits here technically, so maybe the equal sign is a little bit disturbing. I'll do arrows here. But this does diverge. It does not go to any finite real number. And so again, you can kind of see it's very, very slow though, because the natural log already kind of takes its time going off to infinity, right? And then we're taking that, which is going quite slowly, and we're feeding it into yet another natural log. So this is going to be going to infinity, but very, very slowly. but it does diverge. And so you can kind of see why when we were looking at the programming, we didn't really feel like it was going to infinity, right? It doesn't look like it's going to pass a million or a billion or a trillion. And yeah, it does certainly take some time, that's for sure. And so, yeah, you need to plug in very, very large numbers to get it to actually go there. So again, because our improper integral here diverges, according to the integral test, the series we started with shares the same fate. And so usually, for these sorts of questions, I always end with some statement. So I say, since the integral from 3 to infinity of 1 over x natural log x dx diverges, by the integral test, we know that our series going from 3 to infinity, summing up just the integer values, n times natural log of n, also diverges. All right, so there you go. A bit, again, kind of, this is a problem. You say it's maybe not super challenging by any means, but it is the type of problem, right, that you're likely to see for integral test questions, maybe for quizzes and exams, stuff like this, because many of the other ones can be solved using other tests like comparison tests or ratio tests. And by the way, any problem that looks like this, 1 over n times natural log of n raised to some power, whether it's, right, we had the first power, but it could be squared or cubed or anything like this. These ones you can only solve with the integral test. I guess if you happen to know another way to solve them, I mean, try as I might, I haven't been able to find any other way to solve them, even with like a direct comparison test or things like this. But if you know some other method, I'm interested in hearing about it. So please, leave a comment, post on Piazza, something like this. So, all right. Thank you so much, guys, for watching. I hope you have a wonderful night, and I'll see you next time.